So the second method for the analysis of the deflection of the beam is moment area method. So the moment area method is useful for determining the slope or deflection of the beam at a specified location. So for the area moment theorem, we will have to derive two theorems that are bases of the moment area method. So the first theorem deals with the slope, and the second theorem deals with deflection. So basically, for the first moment theorem, so we have here in our figure wherein we will be having our elastic curve AB, and which is an initially straight beam segment. From our figure, it shows here the elastic curve AB. So we have here this is our elastic curve AB, and it is of an initially straight beam segment. So the deformation has been greatly exaggerated in this figure. So we have to take note that the derivation based on our previous discussion of the flexure formula, the two cross section of the beam, we have here the two cross section of the beam, which is P and Q, are separated by the distance dx, and it rotates through the angle d theta relative to each other. Because the cross sections are assumed to remain perpendicular to the axis of the beam, d theta is also the difference in the slope of the elastic curve between P and Q, as shown in our figure. From the geometry of the figure, we see that dx, we have here our dx is equal actually to rho times d theta. So that is equal to rho times d theta. And our rho is the radius, this is our rho, which is the radius of the curvature of the elastic curve of the deformed element. So therefore, our d theta will be equal to dx all over our rho, which upon using the moment curvature relationship. So our moment curvature relationship, we have here our 1 all over rho. So we have here our 1 over rho equal to m all over ei. So this is our moment curvature relationship, and it becomes d theta equal to m all over ei dx. And upon integration, if we integrate over the segment AB, it yields that the integral of d theta from a to b, and that will be equivalent to the integral of m all over ei dx from a to b. So for this one, you have to take note that the left-hand side of our equation is theta b minus theta a, which is the change in the slope between a and b in the right-hand side, represents the area under the m all over e diagram between A and B, as shown in the shaded area in our previous figure 6.4. So if we try to introduce the notation theta B all over A, that will be equivalent to theta B minus theta A, and that can be expressed in this form, that theta B all over A is equal to area of M all over EI diagram from A to B. And this is the first moment area theorem. The second moment area theorem, we are referring to the elastic curve AB in the figure 6.5, wherein we let our T over T of B all over AB, the vertical distance of point P from tangent to the elastic curve at A. So the distance is called the tangential deviation of B with respect to A. So if we're going to calculate the tangential deviation, we first determine the contribution dt of the infinitesimal element PQ, and then use T beams of b all over a is equivalent to the integral of dt from a to b, and to add the contributions of all the elements between a and b. So as shown in our figure a while ago, dt is the vertical distance at b between the tangents drawn to the elastic curve at p and q. So if we try to recall the slopes, which is very small, we obtain from the geometry that dt is equal to x of r d theta, and x of r is the horizontal distance of the element from b. So therefore our tangential deviation can be expressed in this form: the integral of dt from a to b, or this will be the integral of x d theta from a to b. So this is the figure that we are referring with, wherein we have illustrated our tangential deviation of point B with respect to A, and we have make use of that our equation from our P to Q, from our element PQ, then we make use of the tangential deviation of b with respect to a equal to the integral of dt from a to b. So this is our elastic curve of a beam segment, and we have here our bending moment diagram for the segment. So if we try to substitute d theta from our equation, we can obtain that the tangential deviation of b with respect to a is equal to the integral of mx all over ei dx, and that is from a to b. And you have to take note that the right hand side of the equation represents the first moment of the shaded area of the m all over ei diagram in our figure. So this is the figure that we're referring to in our figure, this one. So that is the equivalent value for our equation, and therefore if we try to denote the distance between a and b and the centroid C of this area by x bar of b, and that can be read as the relative to b, so we can rewrite our equation in this manner. So we have now our equation, which is the tangential deviation of b with respect to a is equal to the area of m all over ei diagram from a to b multiplied to bar x over b. So, or bar x as relative to b. And therefore, that is now our second moment area theorem. So we have to take note that the first moment of area, which is represented by right hand side of the equation, is always taken about the point at which the tangential deviation is being computed. So you don't have to confuse that the tangential deviation of b with respect to a with the tangential deviation of a with respect to b. So this, in general, these two distances are not equal. So we have here an illustration. So the tangential deviation of the elastic curve, so if this is our point A, this is our point B, and we draw a tangent line from point A and draw a tangent from point B, so this is referred, that distance from point A towards this tangent line drawn from point B is the tangential deviation of point A with respect to B, and this distance from point B towards the tangential line, the tangent line drawn from point A, is the tangential deviation of point B with respect to A. So we have here our sign conventions. So the tangential deviation with respect to of B with respect to A is positive if B lies above the tangent line drawn to the elastic curve at A, and it will be negative if B lies below the tangent line. And we have a positive theta B with respect to A has a counterclockwise direction, and negative if theta B all over A has a clockwise direction. So we have here our figure illustration showing to us the positive deviation when B is located above the reference tangent, and we have here a negative deviation if B is located below the reference tangent. And we have here a positive change of slope is counterclockwise from left tangent, and we have here our negative change of slope is clockwise from left tangent. So these are sign conventions for tangential deviation and change of slope. So the bending moment diagram by parts. So the application of the moment area theorem is practical only if the area under the bending moment diagram and its first moment can be calculated without difficulty. So the key to simplify the computation is to divide the bending moment diagram into simple geometric shapes. It can be rectangle, triangle, and parabola that have known areas and centroidal coordinates. Sometimes the conventional bending moment diagram lends itself to such division, but each part of the diagram representing the effect of one load. So the construction of the bending moment diagram by parts for simply supported beams proceeds as follows. So we have here our procedure. So we have first calculate the simple support reaction and consider them to be applied loads. Then introduce a fixed support at a conventional location. A simple support of the original beam is usually a good choice, but sometimes another point is more convenient. So the beam is now cantilevered from this support. Then you have to draw the bending moment diagram for each load, including the support reaction of the original beam. If all the diagrams can be fitted to a single plot, do so, drawing the positive moment above the x-axis and negative moments below the x-axis. So we have here our illustration of a simply supported beam ABC, and we start by computing the reaction. So we simply have to compute first for the reaction at point A and at point C. Then we try to introduce a fixed support at point C. So we introduce a fixed support after we have computed for the reaction point and point C. We try to introduce a fixed support at point C. So we have now this illustration, figure B. And afterwards, we simply draw the bending moment diagram by parts. So it starts with our reaction. So that will be 200 times the length, which is 3. So we have here 600. So this will be our m sub 1. Since this is concentrated, so we only have a triangle. Then afterwards, we have a load downward, which is a uniform loading. So 300 times this dimension times 2, the length of the beam of the uniform loading. So that will be 600. So we have here, since this is uniform loading, so we have a curve now. So we have now this curve, and that is negative 600. So this will be our m sub 2. And we have a conventional bending moment. So for this one, we have this figure D. So this one is, we try to, after we have drawn our reaction at point A and point B, we have our fixed support at point B. We choose point B as our fixed support. So we draw our bending moment. So it starts with 200 times 1. So that is 200. You draw the line, you draw the triangle. Then we have a 400 times 2. So that is 800. Then we have 300 times 2, which is downward, so that is negative 600. So this is now our bending moment diagram by parts. This is the second way of drawing our bending moment diagram by parts for our simply supported beam.